Assalamu alaikum. My name is Samiha Ahmed, and this is my video of presenting my poster on the science assessment topic, which is how stars create elements during their lifetime through nuclear fusion. This is my introduction. Nuclear fusion is the process where two light atomic nuclei combine to create a heavier nucleus, resulting in the release of tremendous amounts of energy. The energy released is what prevents stars like the Sun from collapsing. Deep inside a star's core is a pool of protons and electrons. The protons carry positive charge, so they will always repel each other. However, when two protons approach each other close enough, a force called strong nuclear force fuses them together, resulting in one of the protons to emit a neutrino and a positron. A positron is the antimatter version of an electron, therefore carrying a positive charge. Now that the proton has lost its positive charge due to the loss of the positron, it becomes a neutron, which makes it deuterium, a heavy isotope of hydrogen, because now it's one proton and one neutron. Soon, the deuterium will fuse with another proton, becoming a helium-3 nucleus. After that, it will meet with another helium-3 nucleus and fuse together, causing two protons to eject, resulting in a helium-4 nucleus with two protons and two neutrons. The final nucleus weighs less than the original deuterium nuclei. The leftover mass is converted into energy, which powers the star. This type of fusion occurs in the main sequence stage of stars. The triple alpha process also occurs in stars as a type of nuclear fusion, particularly in low-mass stars, where after the star runs out of hydrogen fuel to convert to helium, two helium-4 nucleus fuse to form beryllium-8, which fuses with another helium-4 nucleus to form carbon-12. This occurs in the red giant stage of low-mass stars. Similarly, fusion of carbon occurs, except fusion continues with elements until iron on the periodic table in high-mass stars. Now, what is the importance of the topic? Understanding the process of nuclear fusion is crucial to society and the environment, as it would provide a method of providing ample amounts of safe, renewable energy. Nuclear fission, the opposite of nuclear fusion in that nuclei are split instead of fused, also provides energy. However, a huge disadvantage is that the fission process emits highly radioactive waste, which poses a danger to people and the environment. Nuclear fusion, on the other hand, has no harmful emissions. In addition, a 2023 study on nuclear fusion by the International Atomic Energy Agency discovered that nuclear fusion produces 4 times more energy than nuclear fission and 4 million more times than burning fossil fuels. Another 2022 study at Lawrence Livermore National Laboratory in California revealed that the product of nuclear fusion that is produced as energy is greater than the input nuclei, making nuclear fusion very efficient. Now, since this topic is related to stars, here is a brief intro to a star's life cycle. Stars form from clouds of dust and gas called molecular clouds. These clouds gather, and when their gravitational mass becomes too much, they collapse and turn into a protostar. There are two types of stars, low-mass stars and high-mass stars, and they have different life cycles. First, I'm going to explain the low-mass stars. After millions of years, inside the star's core, hydrogen nuclei fuse into helium nuclei. This provides outward energy, which balances the gravity's inward energy and prevents the star from collapsing. This happens in the main sequence stage. Next, it becomes a red giant. Hydrogen fuel runs out to convert to helium and turns into a red giant as it starts expanding. The triple alpha process will occur and helium nuclei will fuse into carbon. Eventually, all the outer layers will blow away and turn into a cloud of dust and gas called a planetary nebula. It will then turn into a white dwarf, which is the hot, dead core of a star. The white dwarf will cool down after millions of years and then turn into a black dwarf, which is basically the white dwarf, but instead of being hot, it's cold. Now for the high-mass stars. After nuclear fusion in the main sequence stage, hydrogen fuel runs out as well. the star will expand and turn into a supergiant star. In the supergiant stage, the star will fuse together heavier elements all the way up to iron on the periodic table. After that point, no more fusion is able to occur, which leaves the star with no more outward energy to balance the force of gravity, which pulls the star inward. The outer layers of the star will collapse and rebound out in a big explosion and turn into a supernova. A supernova will release heavy elements like uranium, silver, and gold. It will then become a neutron star, which is a very dense ball of neutrons. It is the second most densest thing in the universe, right behind the black hole. The neutron star will eventually turn into a black hole, which is the densest thing in the universe, which not even light is able to escape. These are just some handmade diagrams of the nuclear fusion process and a star's life cycle. Now, I've explained these scientific concepts, but how did I relate these back to my model? Well, the life cycle of high mass and low mass stars are depicted through different sized and colored styrofoam balls in my model to show the different physical properties of the stars, such as their size and color. To show the process of nuclear fusion, magnets were attached beneath the cardboard board as well as beneath colored styrofoam balls representing the protons and neutrons of different nuclei. This was so that they could be moved around to show the fusion process through magnetic force while remaining stable without having a permanent fixture. The balls were colored red to represent protons. However, two of the balls were half colored blue, representing neutrons. This is because when a strong nuclear force fuses two protons together and goes through beta plus decay, which is the process of one proton losing its positive charge and turning into a neutron, to represent this in the model, two styrofoam balls initially connect with each other through the magnets, and one of the half-colored balls is flipped over to the blue side to show the proton becoming a neutron. To show the energy that the fusion process releases, a circuit with a light bulb was attached to one of the star models. After the nuclear fusion process is demonstrated, the light bulb is turned on to show how the process powers the star with energy. After the nuclear fusion process, the star runs out of hydrogen fuel to turn into helium. In low-mass stars, helium nuclei fuse into carbon in a process called the triple alpha process. To display this, small clay balls were modeled to make helium-3, beryllium-8, and the final product, which is carbon-12 nucleus. In addition, the model has an interactive section. There is a small box with a spring attached inside that has a styrofoam model of a helium-4 nucleus attached to it. The top flap of the box basically keeps the box closed. It's attached to two sticks that have two protons attached to it to represent hydrogen nuclei. When the two sticks are pulled together and stuck together, the flap of the box opens up and the spring pops out with the helium-4 nucleus. This interactive section was made to show the fusion process in a simplified manner. When two hydrogen nuclei interact, it eventually results in a helium-4 nucleus. This is the aim or objective of my project, which was supposed to be mentioned right before my explanation of the constructed model, but to build a model displaying how stars produce different elements through nuclear fusion and to show the fusion process as a physical and chemical change in a star's life cycle, which was done. Okay, now we're going to talk about physical and chemical changes. Chemical interactions are defined by processes where chemicals and elements form new chemicals and compositions. Physical changes and interactions are changes to the appearance of a substance without actually changing the internal chemical composition. In nuclear fusion, the two hydrogen atoms collide and a force pulls them together. This is an example of a physical change, as the nuclei collide into each other without changing the composition yet. An example of chemical change, however, is when the two protons become deuterium when one of the protons become a neutron. Here, the composition has changed. Soon, a proton fuses with it and becomes a helium-3 nucleus. The composition has changed again. Two helium-3 nuclei fuse and two protons get ejected, resulting in a helium-4 nucleus. Yet again, the composition of atoms has changed, therefore making this a chemical change. This is just a brief methodology of my project, basically just how I made everything. So styrofoam balls in different sizes were painted and stuck into the base in two linear formations, like coming out in two lines, to serve as stars in their different stages of life. More styrofoam balls are painted red and blue to look like the protons and neutrons for nuclear fusion. Magnets were stuck onto the proton and neutron models and underneath the cardboard base to allow them to move around freely. Clay balls are modeled and glued together to make helium-4 nuclei, beryllium-8 nuclei, and carbon-12 nuclei to show the triple alpha process, which is a process where low-mass stars fuse carbon in the red giant phase. A triangular-shaped hole was cut out from inside a styrofoam ball. Inside the hollow, elements until iron were drawn and colored in, which happens in high-mass stars. A circuit containing a light bulb was attached to a star, and when turned on, it would light up the star to display the release of energy after the fusion process. Labels were made explaining the scientific concepts about nuclear fusion processes and the life cycle of low-mass and high-mass stars, and in general just to guide the audience into what this part does, what that part does. Okay, this is my analysis, and it talks about how I gathered this information and I interpreted this information in a way that I understand. Data for the study was gathered from secondhand sources such as websites and articles. Diagrams are used to expand on our understanding of the fusion process due to the nuclear fusion process being very conceptual and theoretical. Informational videos on the topic from YouTube were watched to clarify our understanding of nuclear fusion, as most sources didn't include the full detailed explanation of the process. Instead, a lot of sites would just say when two hydrogen atoms fuse, it becomes helium-4, without actually explaining the full detailed process. Diagrams and YouTube videos were also used to learn about the full life cycle of stars. Okay, I did my project, so how did it turn out? Okay, so my quantitative data would be: the model accurately displayed the nuclear fusion process using two initial styrofoam balls representing protons to fuse together using magnets. It showed the process of the styrofoam protons turning into one deuterium nuclei, then into one helium-3 nuclei, eventually fusing into four styrofoam balls with two protons and two neutrons, which is the helium-4 nucleus. The model also displayed the triple alpha process, where two helium-4 nuclei were modeled with clay and shown fused together to create beryllium-8, which is then fused together with another clay helium-4 nucleus to form carbon-12. My qualitative data is that the model represented the fusion process with red styrofoam balls representing protons and blue styrofoam balls representing neutrons, and magnets used to connect them together during fusion. The model depicted the energy release following the fusion process through a circuit containing a light bulb that illuminated the modeled star when the switch was turned on. Now for my conclusion. Overall, the model was able to represent the different elements that are produced during nuclear fusion, as well as the chemical and physical interactions during the nuclear process. However, nuclear fusion takes place in real life under very extreme pressure and heat, which is why it has not been yet found how to use nuclear fusion in an industrial scale to provide energy. This is because the high temperatures and pressure required for nuclear fusion only occur easily in space, inside stars. Okay, so due to this, my model was not able to accurately depict the necessity of heat and pressure, therefore maybe perhaps not being able to show the process in the best way possible. Okay, thank you so much for watching and have a good day.